Hi guys, I'm really excited for this chance to talk to you guys. Like Sandy said, I just finished my PhD in scalable cooperation, and I'm really excited to continue my research as a postdoc with Sandy, trying to use complex systems as a lens to study the future of work, AI, and how the exciting cognitive technologies of today are shaping the future of labor in the US. So, of course, technological change is not a new thing. And maybe you're thinking about analogies to the Industrial Revolution, where we saw huge advancements in automating routine physical work. But there are many exciting cognitive technologies today that seem to be qualitatively different. And I'm providing some examples for you here. So for example, just consider the potential to reshape the transportation system in the US as autonomous vehicles become cheaper and more efficient. And also think about computer vision applications and improving the efficiency of medical diagnostics through medical imagery. In any case, we're seeing some evidence that today's cognitive technologies seem to be opening up new frontiers for innovation and entrepreneurialism. However, yeah. I mean, work with data, mostly. Work with information, as opposed to working with material goods. Okay, good question though. Yeah, of course. However, not everyone is necessarily excited about these cognitive technologies. In fact, a recent Pew survey found that a majority of Americans are not optimistic about the future of work and do not think that the economy will create new jobs. So why are people so pessimistic? Well, there are some aggregate trends to support this point of view. For example, if we compare productivity and median wages over the last few years, we can see that in the last couple decades, there's been a separation between these two things. And this has been called the Great Decoupling. And so what this means is that our economy has continued to be more productive, but that increased productivity has not filtered down equally to wages for all workers of different classes. And it's been suggested that technology is a part of this growing divide between people who can invest in capital, labor, and the physical workers. So how does technology interact with labor? We were talking about this big macroscopic trend, but usually technology does something really specific. So I hope I can share with you some sort of fun examples to give you a sense of what I mean. So this is a video from Boston Dynamics. They released this just a few weeks ago. We see this really impressive robot. It's able to balance on these two wheels and maneuver around a warehouse and move up to 30-pound boxes, which it can stack and destack in a very coordinated way. So here, first, it's pretty awesome. Second, it's kind of doing a really narrow thing. Like, good luck using this technology for medical diagnostics, right? It's narrow in scope. Now, let's ask I think some of you have read the comments here, but now let's ask the question, let's say that this technology matures and becomes practical and warehouses start investing in these robots. What does that mean for employment for these warehouse workers? Well, I don't usually recommend turning to YouTube comments for economic forecasts, but you can see that they're sort of pessimistic about it. And why might they be that way? Well, there's this overarching trend when you read the literature on the future of work and technological change, that cognitive workers are augmented by technology. These high-skilled workers, they benefit from technology, but there are low-skilled physical workers who are substituted and replaced by technology. So let me show you another cute example, and we can see if this same thinking applies here. So this is a bit more cartoon, but I think you'll get the point. Here we see an artisanal good produced by a highly skilled worker, and here we see two unskilled workers. But with some technology, we can use these unskilled workers to produce this artisanal good. So let's say, again, that this technology improves and the fake dancing becomes a little better rendered. Let's ask a similar question now. What does this technology mean for employment for the low-skilled workers and the high-skilled dancer in this case? And I think the situation is actually quite different. What I imagine happening is that it becomes cheaper to produce this artisanal good and using these unskilled workers, and that decreases the cost for producing dance, and so more people want dance, and that will boost the demand for these low-skilled workers. because you can produce stamps more cheaply using them in the technology. At the same time, I think that if you can do this with cheap labor, why do it with the expensive ballerina who has to get all this training? I think that the highly skilled ballerina might see decreased employment, while the low-skilled, poor computer science grad students might see increased employment with this technology. So this is actually the opposite of before.
Why use them?
Why? Sorry.
Low-skilled workers, why use them at all? What else to grant in that use case?
Well, certainly this is a cartoon use case. They're trying to demonstrate the use of this computer vision and orientation detection algorithm. So you're right, like if we can just make it artificially, maybe that's the cheapest while still being convincing and entertaining, certainly. But it destroys my story. Okay, so here, like I said, the prevailing narrative in future of work research is this thing called skill-biased technological change, which is the idea that cognitive workers are augmented by technology. So software developers and programmers, they're better off with machine learning algorithms. But physical workers like truck drivers seem to compete with physical technologies. So maybe truck drivers would see depressed employment opportunities as autonomous vehicles continue to mature. But we saw that maybe that story has some cracks in it. And we can look to the literature to find some examples that have been well studied where indeed this narrative falls apart. So for example, surprisingly, national employment for bank tellers in the US increased with the increased adoption of automated teller machines nationwide. And there's two reasons for this. The first seems to be pretty well understood by economists. It's called demand elasticity, and basically ATMs made it cheaper to open bank branches, and so more bank branches opened nationwide. The second reason I find much more interesting, and I was really surprised that there wasn't a good model for this type of thing. Basically, the fundamental skill requirements to be a bank teller shifted from requiring workers with money handling and clerical skills to instead requiring more social skills. And this is because bank tellers today act more as customer service and sales representatives for bank goods and services. So, according to this analysis, if you wanted to completely understand how ATMs impacted bank tellers in the US, you would need to refine your understanding of the skills involved beyond just cognitive versus physical if you wanted to capture this shift onto social skills. So this got me thinking, how can we connect these macroscopic trends like the great decoupling to the specific skills and workplace activities that technology actually performs? So I'm imagining the US labor system looks like this, where there are different labor markets, which in this case I'm thinking about different cities, and there are some cities that are large with greater support for cognitive work, and there are smaller rural cities that perhaps rely more on manufacturing. But we shouldn't be thinking about these labor markets in isolation. There's flows of goods and ideas and workers between all these different places. So how can we compare these labor markets? Well, a natural thing is to look at the employment distribution. But I think if you can go a step further and look at workers' ability to move between different employment opportunities and the connections between different jobs within that labor market, then you're going to get a better sense for workers' career mobility and the economic resilience of that city to changes to the status quo. What factors might allow a worker to move from one job opportunity to the next? Well, we know that skill matching is an important piece. Workers need to meet the skill requirements of an available employment opportunity. And similar to thinking about connections between jobs, we could think about connections between skills to identify interdependencies. For example, trying to approximate skill complementarity. So skills that are complements, like math and programming, tend to be more valuable when a worker has both compared to when a worker has just one or the other. So once we get down to this refined scale, we can look at examples of technologies. So as an example, let's just imagine some machine vision algorithm that impacts the demand for human labor that performs some visual task. We can account for that in a very precise way and look for how other technologies interact with other skills in this really microscopic perturbation sense and see how these perturbations accumulate and diffuse throughout the entire system to create the aggregate labor trends we talk about today. Things like job polarization and bottlenecks to career mobility, and also changes to worker migration and bottlenecks to spatial mobility between different labor markets. So I want to give you just a few examples where I've first tried to use these ideas in a really coarse way to say something about the impact of automation in different US cities. So let's try this out. So to do this, we looked at a few different sets of occupation level predictions for how susceptible to automation different job titles are in the foreseeable future. We combined these occupation level predictions with employment distributions in different cities to produce this on average estimate for each city that I'm calling expected job impact. Now let me be clear that I don't think this impact is really unemployment. I think most of it is changes to the status quo, like what we saw for bank tellers shifting towards social skills. So here in this map, we're coloring cities according to this impact score. And when you squint at it, you see, the large coastal cities are looking a little more blue, indicating that they have less exposure to technology, while the middle of the country cities that are a little smaller are looking a little more orange and red, indicating that they have greater expected job impact from automation in the foreseeable future. So on the right here, we're going to go ahead and sort of quantify this observation. Each circle is a different city. On the x-axis, we have city size according to total employment, and on the y-axis, our expected job impact score. And we find that regardless of the set of job level predictions that we plug into this analysis, we find the same pervasive trend. Small cities face greater impact from automation in the foreseeable future. So what factors might help to explain this cross-sectional trend, the differential impact of automation across cities of different sizes? Like I mentioned, a really natural thing is to look at differences in employment for different jobs. But it's really hard to think about the 1,000 or so different job titles that you get employment for. So to simplify the task a little bit, here I'm using data from the Bureau of Labor Statistics that details very specific skill requirements for different jobs to cluster jobs with similar skill requirements together into job types. So the colors represent these different clusters, and I've highlighted some example job titles from each job type. Now on the right here, we're comparing how does employment for each job type change as I look at one city and switch to looking at a larger city on the x-axis, and the y-axis tells us the employment. And we notice that for most job types, the change in employment is roughly proportional to the change in city size. But there's an exception. It looks like these purple jobs are growing somewhat faster. So one way you might think about this is you need more employment for more purple employment for the last 1,000 people that moved to your city compared to the first 1,000 people. So what are these purple jobs? You can see some examples. There are things like mathematician and physicist and chemist, biologist, computer programmer. There's a bunch of managerial positions in there. So it's sounding like these are the guys who are prepared to use and improve cutting-edge technology rather than compete with it, and some of the workers who coordinate specialists. So this is sounding like a division of labor story. Now here, I want to point out that we were able to gain some valuable insight and distinguish between major job types by incorporating information about the specific skill requirements of these different jobs. So that's how we arrived at the job types, the different colors here. So this encouraged me to go back to my cartoon and think maybe I should focus more squarely on each of these layers and try to actually identify the empirical structure rather than thinking about this in just abstract terms. So to begin with, let's try to describe empirically the space of skills. So to do this, I'm using data from the Bureau of Labor Statistics. They go out and survey workers of different job titles and ask them how important a detailed list of about 300 different skills are to the completion of their job. We can aggregate these responses across workers to arrive at an on-average importance of each skill to each job. And by looking at how pairs of skills co-occur as important, we can relate skills to one another here. So in truth, the methods we're using are really similar to the product-based analysis from Cesar Hidalgo and Ricardo Hausman. So they were looking at national economies and their exports, and they related exports to one another following a really similar scheme. And this is what they found. This is the product space. And you see that it has this really sparse periphery and this really dense core. They found that small national economies tended to export the extraction goods on the sparse periphery of the space, while larger economies were better able to export the complex goods like car parts and computer parts that occupy the dense center of the space. So in our analysis of occupations and skills, we're using a really similar methodology, and so we might expect to see something different, or see something similar. But let's see what happens when we actually connect our skills into a network. This is actually what we get. Now, this is a completely data-driven methodology. The fact that there's two clusters here is totally a result of the data. There could have in principle been no clusters, like in the product space where there's this dense core and sparse periphery, or 10 clusters. But the data is telling us there's two major skill types. And you can see them represented by this a densely connected set of skills on the right here, which represent sensory physical skills, so things like manual dexterity, low light vision, strength, and stamina, which are separate from this other clump of skills on the left, which tend to be social and cognitive, so things like mathematics and complex problem solving and programming, but also persuasion and negotiation. These are all skills that occupy the left side of this space. So this is a pretty interesting data-driven result, but what does it allow us to say about aggregate labor trends? So to investigate here, we're looking at the distribution of skills and their importance across different occupations and using a method to identify skills that are characteristic of each job. So these are skills that distinguish that job from other occupations based on their workplace requirements. And we can use this information to project occupations onto the skill network. So here I'm coloring in with black circles the skills that are characteristic of dishwasher, and we can see that this job is very sensory physical. We repeat this for occupations with higher and higher annual wages and observe a pretty pervasive trend. There's this smooth transition from relying on sensory physical skills to instead relying on social and cognitive skills. We can do something similar for cities. So here we combine the skill requirements of jobs with employment distributions in cities to produce a skill distribution in cities and identify the characteristic skills of different cities and then project those skills onto the network. So in a somewhat similar way, we find that cities with higher median household incomes, which also tend to be larger cities, exhibit this smooth transition from relying on sensory physical skills to instead relying on social and cognitive skills. So this, combined with some other more detailed analysis, was pretty rewarding for me because it allowed me to connect this skill polarization that the data revealed to us and descriptions of job polarization that already exist in the literature. In particular, I think there's a connection between David Otter's hollowing of the middle class, which he describes as a distinction between high-skilled work and low-skilled work, but what he actually measures is annual wages. On the other hand, we started with no assumption about what the world looks like and looked at specific skills, but we're able to meet him halfway. So I think that these represent the low skills, and these skills represent the high-skill work that David Otter is talking about. But we can gain some new insights as well by looking at the specific connections that define this network, by looking at the topology here. In general, we find that workers move between employment opportunities that have similar skill sets on that network. So they don't jump randomly about the skill network, they move locally and smoothly. So when you combine this insight with the skill polarization we uncover on aggregate, we can see empirically that there are three major types of behavior. There are workers who begin in occupations that rely strongly on sensory physical skills, and they seem to be stuck moving to other physical work. There are workers who leverage social and cognitive skills, and they tend to move to other social and cognitive work. And then there's this interesting third group. These are workers who are in occupations that straddle between these two skill sets. And these workers seem to be unwilling or unable to transition to higher earning social and cognitive employment. And actually, these three modes of behavior are represented in national employment when we bin employment according to its reliance on social and cognitive skills. So this is some evidence that we can use this empirical structure we identified to describe the space to say something about labor dynamics in the next layer up, so how workers are moving between different skill sets throughout their career. And this was rewarding, so I figured let's try this again. Let's try to identify the empirical structure to describe this middle space and use that to describe dynamics in the next layer up. So to do this, we're going to adopt a similar methodology from before, but instead of connecting skills to one another, we're going to connect job titles to one another based on the similarity of their characteristic skills. So how does our skill similarity score allow us to capture, say, the rate of workers transitioning between job pairs? And as a baseline, we're going to compare it to a random mixing model using just national employment. So that's that first model there on the left, and you can see that usually this model accounts for about 15% of the variance in how workers are transitioning between job titles based on skills. And we see that when we augment this random mixing model with traditional coarse labor categories, for example, looking at measures for how cognitive and physical or routine and non-routine an occupation is, it doesn't really add anything to the baseline random mixing model. However, when we instead leverage the refined skill categories that we're using in our skill network, we do see an improved performance from the model in its ability to predict how workers are transitioning between employment opportunities. So that was encouraging, and it led me to try to encode that information in a way that allows us to describe the whole space of jobs. So here, this is a network of job titles, and jobs are connected if they have high skill similarity scores. So they have a lot of shared characteristic skills. Similar to the skill network, this job network is polarized, and when we look at the skills that define the jobs in these two sets, it seems to be a distinction between cognitive occupations and physical occupations. But if you want a more traditional thing to measure against, these occupations are also distinguished in terms of their annual wages. So that's cool. Can we again use this structure to say something about the labor dynamics in the next layer up? And in particular, how workers are moving between different labor markets, different cities in this case. So to do this, we first need to relate different cities to the job network. So here, we're going to use the employment distribution in each city. We're going to use a measure called location quotient, which is a long-standing measure that allows us to identify the characteristic occupations in different cities. And then we're going to project cities onto the complete job network by coloring in just the occupations that are characteristic of that city and coloring in the connections between those characteristic occupations. So here's an example. This is Boston. Here's another city, Houston, Texas. So how can we use this information to relate and compare the employment in these two cities? So a simple way I've thought to do this is to create what I'm calling an overlap network. So here it's our job network, but we are coloring in the occupations that are characteristic of both Boston and Houston, as well as the connections between those shared occupations to create this overlap network. Here's another pair of cities. We're looking at Madera, California, and Seattle, Washington, as well as their overlap network on the right here. So let's try to compare these overlap networks. When I do this, there are two features that jump out to me. The first is just the number of colored in circles is different. There's more colored in circles up there. And this is a simple thing to measure. It's just the number of occupations that are characteristic of both cities. The other feature that jumps out to me is the density of connections between those shared occupations. The network on top is more densely connected than the sparser network on the bottom. And you'll remember that we were using the edges in this network. We were connecting jobs that had high skill similarity score, and we saw before that occupations with high skill similarity had greater rates of workers moving between them. So this means that overlap networks that have greater density of connections between them might represent greater opportunity for workers moving from one labor market to another labor market. And that could underlie and allow us to predict spatial mobility. So let's test this out. Here, I'm introducing a measure called city tightness, which uses the skill similarity scores between pairs of jobs and the employment data for different cities. So let's see, how does this model allow us to predict the number of enplaned passengers flying between city pairs over 2015, and also census migration rates in 2015 between city pairs? As a baseline, we're going to start by looking at the gravity model, which is sort of the usual baseline model here. It uses just the size of each city and the spatial distance between those cities. First, we're going to consider augmenting this gravity model with just the overlap, which is just, in this case, the number of occupations that are characteristic of both cities. So it's just this really simple measure. And even just looking at this type of employment information yields improvements in the model's ability to predict spatial mobility. However, the best performance is achieved with both models on the right here when we also include skills information in addition to employment information in the model. So again, this is some evidence that we can use the structure that describes this middle space to say something about the employment dynamics in the next layer up. So we started the talk looking at this cartoon, and I think we've gotten to the point we can fill in the cartoon with some actual empirical structure here. So we have our 3 layers from before. We have our polarized skill network on the bottom. We have our job network in the middle, and then we have cities at the top. And I suggested earlier that once we got to this stage, we could look at some technology, a specific one, and look at the workplace skills and activities that could be impacted by that technology and see how these little perturbations from other technologies and skills accumulate and diffuse throughout the whole system. And I'm excited to continue working on this. And thinking about this, I'm encouraged by some ideas from ecological resilience. So in ecology, we have a similar notion to equilibrium analysis that economists use today, but it also turns out that when you look at how different species interact mutualistically within an ecosystem and look at the density of connections of this mutualistic network, you can use that information to predict the ecosystem's health and its resilience to negative impacts like rising temperature or rising acidity levels that might make certain species go extinct. So by analogy, maybe we can look at the density of skill sets that are supported in a city, or the density of connections between job titles in a city to say something about the economic resilience of that city to changes to the status quo, to the removal of demand for certain skills, for example. This type of analysis also opens up some opportunity to improve forecasts of the future of work. We have a really clear framework for distinguishing between intercity and intra-city dynamics, as well as the changing nature of work within a job, like what we saw for bank tellers. And when we can disentangle all these different pieces in a really precise way, I think we're providing some new tools to policymakers and to individual workers who are trying to improve forecasts of the future of work. It also opens up the potential to consider some new sources of skills-level data. So for example, we could look at real-time online job postings to see which skills are in demand, and we could look at data from LinkedIn or resume data to see in real time how individual workers are advertising their skill sets over time and how those skills change to reflect the demands of the current day. I'm also interested in looking at patent data as maybe a noisy signal of which technologies might reach maturity soon, and if we can connect technologies to the workplace activities and skills that that technology will do, then we can plug that into this type of analysis and use that information for forecasting the future of work. I think there's a lot of interesting ways we can use insights at the level of specific workplace activities to understand how technology is changing the nature of work. Maybe we can make more efficient worker retraining programs. We can better identify which types of work are likely to be automated and what that type of automation means for those workers or maybe those cities. We can better investigate what leads to economic resilience in cities. What types of skills and what types of workers should you be supporting to make your local labor market more resilient to technological change or to offshoring of work, for example. And finally, if you're a company and you're trying to invest in make a major technological investment, how do you prepare your workforce and your production line to maximize your returns on that investment as quickly as possible? So these are some areas where I think specific skills and the analysis I've presented to you here can give us some new insights.
Super. Good. Time for a few questions. Could be on anything, this, but the whole thing. Yeah.
I noticed that, Notice that in your percent of jobs impacted analysis, there was a pretty clear trend, but even on the low end, it looked like it was at 55%. It looked like it was varying between like 55 and 70. Can you tell how that's defined? Is it really as stark as that 55% of jobs at the minimum are going to get radically impacted? What's the actual definition there?
Yeah, so exactly what that lower bound is depends on the occupation level predictions you plug in there. And I was using estimates from a well-cited study from Oxford University that's authored by Carl Fry and Michael Osborne for that visualization in particular. So yeah, if we plug in their estimates, and depending on how you interpret those estimates, we're interpreting it as most of that exposure represents changes rather than the deletion of employment, then yeah, about half of work in those cities is susceptible to change. I know that this is not crazy also. I don't have slides for this, but I know there's some ongoing work with Eric Brynolfsson where we're looking at specific technologies, like look at supervised machine learning and look at the activities that that technology can do in particular. Now, what percentage of workers say that that activity is important to them? And even when we look at machine learning in a really narrowly defined way, you get estimates that are up there, 30%, 40% of labor as defined by like employment-weighted workplace activities are exposed